它这个不是那个的。你可以先把那个先打开，打开我先介绍一下这个。现在声音打开了吗？好的，那现在刚好是10点，那我们就现在开始。看一下，请各位老师，然后各位同学，各位在线上和线下的老师同学们，大家上午好。然后首先非常欢迎大家来参加我们第40期的北京气象学会的专家讲座。那也是非常感谢我们各联合承办单位和一些直播平台长期以来的支持。那我们北京气象学会的这个专家讲座呢，是从21年6月份开始创办以来呢，已经举办了39期。通过腾讯会议、知乎和扣享学术等媒体平台，已经服务了公众逾这个60万人次。那我们也是在这种精心的搭建一个开放共享的学术交流的平台。那我们这个就是本期的讲座的这个报告的一些回放视频呢，也会在这个北京气象学会和我们城市院的这个就是网站上有共享，来供更多的这个就是在事后可以来听取和调阅。那我们也可以通过这个知乎和扣享平台来观看一些视频的回放。然后我是今天讲座的这个主持人是就是这个北京城市气象研究院的苗世光。那我们今天呢是这个非常高兴的来邀请到了我们美国波士顿大学就是地球与环境系的副主任，也是这个机械工程系的这个副教授的这个李丹博士。然后他呢是同时也是担任就是这个波士顿大学城市项目的副主任。然后他是13年获得普林斯顿大学土木和环境工程系的博士学位。那13到15年呢是在这个普林斯顿大学来做博士后的研究。16年呢是到这个说错了，是在普林斯顿大学做这个博士后研究。然后16年呢是到这个波士顿大学。那他就是说主要是在对于这样一些大气边缘层的动力学和热力学的就是这样一些科学认识方面的研究，以及呢相关的成果在这种解决现实世界的这种就是可持续发展挑战方面的一些应用的研究。那他在就是也是这种就是说先后就是获得了就是红宝基金会的红宝资深学者奖，以及城市气候协会2022年度的Timothy奥克奖，以及2023年度的美国地球物理联合会的全球环境变化早期职业奖，是不知道中文怎么说，应该是这种早期职业奖是吧？然后这个英文是叫这个 Early Career Award。对，然后他今天这个报告的题目呢是这个就是连接应用气象和气候科学的桥梁，就是通过几个城市的这个就是案例然后来给这样方面的一些报告。然后那我们下面就欢迎这个就是李丹博士来做报告。
好，首先谢谢苗老师邀请，也非常高兴，这是第一次来我们之前我的这个就比较方说，我这个报告叫breaking the gap 啊。我之所以选了这个主题，跟我2023年在中国有点关系。当时我记得好像是因为在美国单位在那写说他们咱们这个形式跟面这样这个有机的关系，就当时就在跟他们讲这个，我以前做主配的时候也都是面做的这个，那我现在就 现这个重，想创业方向的一个真的是不好的问题，所以我就特别就开始往这个方向思考，就把我们最近一段时间做的工作总结一下，想让大家就看一看我自己是怎么科学，刚开始刚做董事和之后的时候，慢慢的演变到现在的我讲报告的时候用英文，还是用中文讲，这个有点可能一上午就讲，那个很多单词我不太会用中文但是你们如果有问题的话，可以打断，可以问，有问题的话可以跟我。So the as I just mentioned, urban meteorology and climate policy are usually viewed as a branch of meteorology. 人这样的是推荐的，就是一直来说认为这个命性的一部分。This is because urban meteorological and climate information is widely used in many real-world applications, such as the design of buildings, the operation of drones, and the development of climate adaptation plans at city scales. So the practical value of urban meteorology and climatology cannot really be disputed. In about 2005, there was a paper published on BAMS titled Applied Climatology, The Golden Age Has Begun. And here I'm showing you the number of articles on one small topic under the umbrella of urban meteorology and climatology, that is using numerical modeling to assess the effects of urban heat mitigation strategies. You can see that the number of articles on this one particular topic under urban meteorology and climatology has been increasing since about 2005 quite rapidly. It sort of corroborates the idea that the golden age has begun for applied meteorology. One of the key reasons, in my opinion, that the number of articles on these topics has been increasing since around 2005 is also because we are approaching the problem from the applied perspective. For example, when it comes to urban heat mitigation strategy, the question usually is, what are the impact of those heat mitigation strategies? And we would use numerical models to assess the impacts of those heat mitigation strategies using sensitivity experiments. And whenever we change a city, we change a study period, or change the mitigation strategy configuration, penetration rate, we essentially generate a new study, because from an applied perspective, that is a new study. In fact, when I was doing my PhD was between 2009 and 2013, and then I did my postdoc from 2014 to 2015. So you can see that my study period, or the period where I was doing my PhD, was mostly actually within that period. Can you see the mouse?
可以用这个对，
但是网络上可能
可以用鼠标吧，用鼠标。
用鼠标，你用鼠标的话，
把它换成一个激光笔，右键对，指针选项，对，激光笔，对，第一个。
Okay. So you will see that actually some of my studies during that period are actually studied, approaching the problem from the applied perspective. But lately I have been thinking about this problem, as I mentioned earlier, motivated by some of the conversations actually I had here in China. And also a lot of the people are thinking about this problem as well. So, from not only from the urban perspective, but more from a broad perspective of the gap between a lot of the, simulations that we're doing, as well as understanding when it comes to climate. Some of these papers are listed here, and they really motivate me to rethink some of the research that I am doing myself, which focuses on, of course, more specifically on urban climate modeling. So today I'm going to use two examples, and they are quite widely studied in the literature. One is the effects of white roofs and a mitigation strategy. And the second is the effects of anthropogenic heat flood, which is the energy generated by human activity. And I'm hoping to show you that using these two examples, how we can actually utilize some of the climate science concepts that can help us to reframe the questions that we're addressing in urban meteorology and climatology. So the starting point of my presentation on the first example is this so-called albedo cooling effect. So you can see that this was a review paper by my friend Scott Freinhoff in 2021. And what they did was they looked at the literature and found all the articles that use the numerical models to quantify white drift effects. And to quantify the white drift effects, they proposed that we should use this concept called albedo cooling effectiveness, which is defined as minus delta T, where delta in my presentation always means a change, and in this case is the change due to the albedo change in the roof, divided by the albedo change at the scale at which the temperature is defined. So for numerical models, the temperature is usually defined at the grid set level. So the albedo change at the grid cell level is the albedo change over the roof multiplied by the roof fraction. So when they use this index to compute the ACE across different studies, they found that the ACE values range between 0 small values to as large as 20, with the mean or median values that is on order about like 3 to 6 ish. One of the papers, as I mentioned earlier, was actually written by me. That was like the lead to 2014. So that was like more than 10 years ago now. You can see that my values range between about like 2 to 5 ish, with a median value of about like 3. So that's the state of art, actually. You can see that this was like 2021. But there are two issues with this ACE. The first issue is that the reason we compile a list of the ACE values in the literature is that we're hoping the literature values will have some guidance value for us to use in other cities, other places. What that implicitly requires is ACE values don't have a lot of spatial variability or temporal variability, or hopefully if they're constant, that would be great. We can just take ACE values from the literature, we can apply it elsewhere. But ACE values cannot be constant, right? A simple thought experiment tells you that it has to, at the very least, vary with incoming solar radiation, or the solar radiation that the roof receives. In places where the roof receives a lot of solar radiation, painting the roof white is going to be more effective or produce more cooling effect than in places where the roof receives less solar radiation. That's very natural to think. So we cannot just take the AC values from Phoenix and apply it to Boston. That's because Boston and Phoenix don't have the same amount of radiation level. The second issue is that oftentimes this ACE values, at least in the paper, is defined based on near surface air temperature. Like for example, this classic 2-meter air temperature that numerical models tend to produce. But the near surface air temperature, the change of that is quite difficult to interpret, especially over city, as you will see in an example. So let me show you a specific example to kind of like illustrate these 2 points, and then I'll come back to how to address these two issues. So a typical study for assessing white drift effects, like the one that I did 10 years ago, was like that. So we use a numerical model. For example, here we're using the weather risk and forecasting model, or coupled with the single layer urban canopy model. You don't have to use this model. I'm just using this model to illustrate the problem.
in this particular model, you can see that sort of the urban environment is represented by, a pervious part and then an impervious part, a pervious part and then an impervious part. The impervious part is treated using a sort of like urban canyon structure. So you have like a building and then have a canyon floor. You can see that the roof is explicitly represented in such a, idealized modeling structure, right? So what you can do is that you can increase the albedo of the roof. You paint it white, of course, in the modeling world. And once you do that, you probably would expect the temperature to drop, right? When you increase the albedo of the roof. So, for example, if the temperature profile within the lowest level of the atmosphere looks like this originally, if you implement the white roof, you probably would expect the surface temperature, assuming that this grid has a well-defined surface temperature. The surface temperature is probably going to drop. And this cooling signal will propagate up to the atmosphere, right? So, for example, the atmospheric temperature that is above the canyon is often simulated by the atmospheric model will also be dropped because it feels the cooling signal. And then this, 2-meter air temperature, which is oftentimes you can think of as essentially an interpolation between the surface temperature and the atmospheric temperature at the lowest atmospheric grid, which is typically 20 to 50 meters these days, will be also dropped. And that's very intuitive. Well, sometimes the atmosphere does not behave exactly according to what we, according to this simple picture. So, for example, when you introduce white roof perturbations on the land, the atmosphere may start to behave a bit, chaotically first, at least. And locally, sometimes the atmosphere actually warms up because you induce certain advection that will transfer warm air elsewhere to this grid cell. So the atmospheric temperature might actually warm up. As a result, the near surface air temperature, that is the interpolation between these two grid cells, sometimes actually might be increased when you have white roofs, which is a bit counterintuitive, but it actually sometimes happens. So with that in mind, let me show you actually a case study that I did over Boston. So to orient you a little bit, the middle of the figure is basically Boston. The size of this figure is typically about 100 by 100 kilometers. On the right is like the ocean, and on the left is the land. If you see a color, it means that the Wolf model treats this as a grid cell, as an urban grid cell. So we have the white roof effects in those. So here I only show the urban grid cell results. What we did is 1 kilometer resolution over a period of heat wave, 5 days, and then we did 2 runs. In the control run, we used the albedo of 0.2 for the roof. In the high albedo one, we used the albedo of 0.6. And if you take the difference between the two simulations in terms of this near surface air temperature, the 2-meter air temperature, this is the difference. And these temperatures have been averaged over this 5-day period. You can see that most of the places, as expected, you see cooling signals. Not too surprising. If you increase the albedo of the surface, you should expect the cooling signal. And in those places, when you compute ACE values, according to the formulation that I just showed you, you get ACE values, that are on the order of mostly between 0 and 6. The ACE values are negative, or in other words, the white roof effects actually warming in certain grid cells, not a lot, but some in this part, which is a bit peculiar, right? Why do we see warming effects of white roofs? More importantly, if you look at the spatial pattern of the ACE values are not constant. You can see that, sometimes it's like 0 or even negative, sometimes it's over 10. But the median value is about 2.2, which is, reasonably agrees with the table that I showed you early in the review paper. But it shows very strong variability. We have to understand this spatial variability. Otherwise, the ACE values reported in the literature are useless because they will have no transferability across different regions. So the question is twofold: why we see warming effects of like the white cubes. Second, how do we understand the spatial variability of the ACE value? If they vary a lot, then how do we even predict that? So let me start with the first question, which is the warming effects of the white cubes. And to understand this, we can do a decomposition analysis. So we decompose the change of the near surface air temperature due to white cube effects into different contributions. And I did this separately for grid cells that you see cooling effects, which is 91% of the grid cells. And then the grid cells that you see warming effect, which is only 10% for the cluster region that I showed earlier in the previous slide. So here, right? So basically around here. Okay. Without going into the details of this decomposition analysis, let me just tell you how to interpret them. The first two bars are one computed by Wolf, one computed by this decomposition analysis. And if they agree with each other, it means that this decomposition analysis is working reasonably. So you can see that immediately that it works better for the case where you have the cooling signal than the case where you have the warming signal. And there are two reasons. One, the signal is smaller in this case. So on the left, the signal is about minus 0.2. On the right, it's like 0.05. Second, the number of data points is much smaller. So on here, you have 91% of the grid cells showing the cooling signal. Here, you only have about 10%. So that is also why the decomposition analysis is not working as good for the as good on the right as compared to the left. But it's still, reasonably good. Now the contribution is coming from the 5 different bars afterwards. So the first bar is the roof surface temperature change. You can see that it's a negative value. It means that the roof surface temperature is reduced. As a result, it caused the near surface temperature to be reduced. That's understandable, right? Very intuitive. And the second bar is the atmospheric temperature above the canyon. So the one that I showed you at the top of the canyon. So you can see that when the roof surface temperature is reduced, the atmospheric temperature above the canyon is also reduced. As a result, the near surface air temperature, which is almost an interpolation of these two, is reduced. So the left is basically the picture that I showed you earlier. It's basically this scenario where the surface temperature reduced, air temperature above the Earth canyon is reduced, near surface air temperature reduced, classic. The second case is the roof surface temperature is still reduced. And that's not too surprising because you increase the roof albedo. So the roof surface temperature reduced. But the atmospheric temperature is actually increased. As a result, it caused actually the near surface air temperature to increase its temperature, which sort of like coincides with this scenario. And I'm not going into the details of why the air temperature here is increased, even when you have cool roofs. That's more related to warm air advection that is caused by the perturbations that you put on the surface. But after looking at this figure, one thing that comes to my mind is that why do we have to focus on the near surface air temperature from a scientific perspective? We should start by looking at the surface temperature from the roof. If we cannot understand the roof surface temperature change, there's no chance for us to understand the near surface air temperature change. Because, first of all, the cooling signal is coming from the roof. Second, look at the roof surface temperature. At least it is consistent across these different cases. It's always reduced. So it must be a simpler problem. We should address the simpler problem first, and then move to the more complicated problem. So after realizing that, let's just say, well, let's redefine the ACE values. Let's use the roof surface temperature to define it. Well, what we're going to study is a simpler case where the subscript S indicates the surface. In this case, the roof surface. So what I did was ask the Wolf to give me the roof surface temperature outputs, the control run, the high albedo run, the difference between the two, you can see the roof surface temperature drops quite a lot. And it's always consistently negative, as you would expect, because you increase the roof albedo. And the surface temperature drop is much stronger. It's on order like, a few Kelvin compared to the air temperature. And air temperature drop is on order like 0.5 Kelvin. So in this case, when you compute the ACES values, at least you don't have the surprising value. You only have positive value. So now we can focus on explaining the spatial variability of the ACES. If you can do that, at least you move the problem forward a little bit. Not that before you address the problem, you move the problem a little bit forward. So now the question is, what's causing the spatial variability of the ACES value in a domain that is as small as 100 by 100 kilometers, right? It's like, half of Beijing or just over Beijing. If you paint the roof white over the western side of the Beijing versus the eastern side of Beijing, you actually get different cooling effects. I mean, it's natural to ask the question, what's causing the spatial variability, and can we understand the spatial variability? Well, that's related to the first issue that I sort of mentioned. Some of you probably have guessed. One of the reasons that you see actually spatial variability in this value is because the different places receive different amount of solar radiation. So if you just plot the ACES value as a function of the incoming solar radiation for the roof surface, not too surprisingly, in places where you receive more solar radiation, painting the roof white is going to cause the surface temperature to drop more compared to in places where you receive less solar radiation. That's quite intuitive, and the Wolf results perfectly illustrate that, right? These two have a very good linear relation. Well, now, after seeing that, you can say that, okay, most of the spatial variability in ACES is caused by the spatial variability in the incoming solar radiation. Why don't we normalize the y-axis by the x-axis? Let's see what happens. So you can normalize the ACES by the incoming solar radiation. Now you can even define, so what I did is I defined this as a new concept called albedo cooling sensitivity. And I'll tell you a little bit why we call it a sensitivity instead of effectiveness. And it's nothing but the change of the roof surface temperature divided by the change of the roof albedo multiplied by the incoming solar radiation with a negative sign, so that all the ACE values tend to be positive when you increase the albedo. So once you do that, you can find that the spatial this is the simulated pattern across the Great Boston area. Again, this is Boston. On the right is the ocean. On the left is the land. If you see a color, it means it's an urban grid cell. So you can see that two things happen. First of all, the unit changes. It used to be Kelvin, because it's the temperature divided by the albedo. So the unit of AC is Kelvin. But the unit of ACS is Kelvin per watt per square meter. Second, you still see some spatial variability. I mean, the spatial variability is not a lot, but it still ranges from like 0.03 to 0.045-ish. So even after we normalize the incoming solar radiation, there is still remaining spatial variability in our domain. And what's causing the spatial variability in there? Because supposedly we've already removed the spatial variability of the incoming solar radiation. Okay, to understand this point, now I have to tell you a little bit of the theory, that is the surface energy balance. To understand this problem, you need to know a little bit about the surface energy balance. And the surface energy balance describes nothing but the energy gained by the surface has to be equal to the energy transferred out of the surface if you think of the surface as an infinitely thin layer that cannot store any energy. And you can write the surface energy balance equation this way. On the left, you have the energy gained by the surface, mostly coming from the radiation, incoming short radiation, incoming long wave radiation. But here we want to subtract the reflected radiation, right? So we multiply the incoming short radiation by 1 minus alpha, and we multiply the incoming long wave radiation by epsilon. By the way, alpha is the albedo, in case you haven't figured out. Alpha is the reflectance for the short wave band. Here we multiply it by the emissivity for the long wave band, because Kirchhoff's law tells us that the emissivity is basically also the absorptivity for the long waveband. On the right, you have 4 different terms: the sensible heat flux, or the heat taken away by the wind through convection; the latent heat flux, associated with the evapotranspiration process. For the roof sometimes still evaporates. After rain, the roof will hold some water on the roof, and that part of water evaporates. So there is still some evaporation going on the roof. There's a conduction into the interior materials, and then there's emitted long-wave radiation, which is expressed here using the Stefan-Boltzmann law, where sigma is the Stefan-Boltzmann constant. This equation may look slightly different from the equation that many of you are more familiar with, which is that we will be put this emitted long-wave radiation to the left-hand side equation. If you put the emitted long-wave radiation to the left-hand side equation, then the left-hand side equation becomes the so-called net radiation. I did not do that because I want to emphasize that each term on the right-hand side equation is a function of the surface temperature. But the terms on the left-hand side of the equation are to the first order, not a function of the surface temperature. So that's the reason why we write the equation this way. And to make the math easy, I'm going to assume that each term on the right-hand side of the equation is a linear function of the surface temperature. So they can be all expressed as some number, which represents the slopes of this linear function, multiplied by the surface temperature plus some c, which represents the intercept. And this is just, for some of these terms, it's just a simple reorganization of the typical parameterization that we use in meteorology. For example, sensible heat flux is often expressed as rho Cp, air density, multiplied by the heat capacity of air at constant pressure, multiplied by some sort of heat transfer coefficient, and then multiplied by the difference between the surface temperature and the air temperature. If you expand this equation, it looks basically like a linear function of the surface temperature. So lambda h defined here is basically rho Cp Ch here. The other heat fluxes are not always linear functions of the surface temperature, but we have mathematical tools that allow us to linearize those functions. For example, this emitted long-wave radiation is the surface temperature to the power 4. It's not a linear function. But we can linearize this surface temperature to the power 4 around air temperature. And then we will get a linear function of the surface temperature, where this lambda ELW, where ELW refers to emitted long-wave radiation, is equal to 4 epsilon sigma T to the power 3. And these lambdas have units of watts per square meter per Kelvin. They can be interpreted as heat transfer efficiencies. For example, if you work in engineering, I have an appointment in Department of Mechanical Engineering, so I know that the engineering people call this lambda H basically the convective heat transfer efficiency. But if you're more familiar with the climate change literature, they're actually equivalent to the climate feedback parameter. For example, this lambda ELW basically represents the strength of the so-called Planck feedback. And the Planck feedback essentially means that if you give the Earth system a bit more energy, the Earth system has to increase its surface temperature so to emit more long-wave radiation back to the space in order to balance the energy that you give to the Earth system. Perhaps a better way to understand the surface energy balance is through a figure instead of all these equations. So here I'm plotting the total fluxes on both sides of the equations as a function of the surface temperature. As I alluded to earlier, the left-hand side of the equation is treated to the first order, not a function of the surface temperature. So when you plot it as a function of the surface temperature, it's just a flat line, which is what this black line represents. Since I have linearized every single term on the right-hand side of the equation, then the right-hand side of the equation is just a linear function of the surface temperature, which is what this red line represents. Now you can immediately see that the surface temperature has to be at this intersection, because it is only at this intersection that the left-hand side of the equation is equal to the right-hand side equation, or the two curves meet. So that's where the system is in energy balance. Now you can think about, what if we perturb the system? What if we, for example, increase the albedo of the surface? like what we did with the white roof. You essentially bring down the black line because the black line represents the left-hand side equation, and the left-hand side equation is a function of albedo with a minus sign. So as you increase the albedo, the left-hand side equation drops. And if you assume the red line stays where it is, you get a new intersection, in this case, a reduced surface temperature, as you would expect. So increase the albedo, reduce surface temperature. You can do this a bit more rigorously. You can say the change of the albedo is dot alpha, then the change of the black line to the first order is the incoming solar radiation multiplied by minus dot alpha from the left-hand side equation. From simple geometry, you can back out the change of the surface temperature, which is nothing but this term divided by the slope of the red line, which is the sum of the lambda. So now we have a formulation that looks like this from the surface energy balance. And if you put the incoming solar radiation multiplied by minus dot alpha to the left-hand side equation, it simply becomes the albedo Coulomb sensitivity that I defined earlier. Now you can see that. Now you can see two things. One, why this is called sensitivity, because it's basically climate sensitivity. It's the temperature change of the problem normalized by the forcing of the problem. The forcing in this case is coming from change of the albedo, and the temperature we're focusing is the surface. So it's not a climate sensitivity defined by the climate people, but it's the local surface climate sensitivity. The temperature and the forcing are both defined at the surface level, not at the top of the animal. But that's fine. We can still call it a climate sensitivity. It's a climate sensitivity. Second, you can see why this thing cannot be a constant, because it's related to a bunch of climate feedback parameters, just like the climate feedback parameters are not constant in the climate. They are not naturally constant, or they vary spatially. So that's why the ACSS shows strong spatial variability, even in the domain that we're simulating overpass. So the third thing that you can argue is that we actually connect the climate sensitivity to the climate feedback parameter. Just like the climate change people, with doubling CO2, you have the climate sensitivity. The reason we are studying all this climate feedback is we want to figure out how the climate sensitivity looks like in the climate model. Right? Same here. We have the climate sensitivity. We have 4 climate feedback parameters, with the Planck feedback being one of them. And in the Wolf simulations that I showed earlier, now we can explain the spatial variability of the ACSS that we showed earlier. It ranges from 0.03 to about 0.05 that I showed earlier. With a unit of Kelvin per watt per square meter. The reason that in this model you see spatial variability in this ACSS is mostly related to the spatial variability of the convective heat transfer. And the convective transfer is related to things like wind speed, thermal stratification of the atmosphere, and it's a decreasing function of lambda h as the formulation that as the substandard balance model predicts. In fact, the black line is that you assume all the other lambdas is a constant. The only thing changes the lambda h. And the decreasing effects is because in places where you see a lot of a very strong convective transfer, the roof already has a natural mechanism to take the heat away from the roof surface. In other words, if you want to paint the roof white, you don't want to paint the roof white in those places because the roof already has a mechanism to take the heat away. So if you do paint the roof white in those places, then the effects of white roofs will be less compared to in places where the roof does not have this natural mechanism to take the heat away. That's why it's a decreasing function. You can also see that it not only explains the spatial variability, it also explains the variability across different simulations. So we did the Wolf simulation. For those of you who are, familiar with Wolf, in Wolf you can change certain physical parameterization, which give you a different, essentially, simulation. You can see that for all these different colors, which represent different Wolf simulations, this model, which comes from the substandard balance, works within the Wolf. In this simulation, the other numbers are not important. However, if you do the simulation other places, the numbers might become important. So let me show you another example. In this case, we're doing it over the entire globe. So we take the so-called community land model, we run the model globally, and for places that you see color, it means that those grid cells are urban grid cells or have urban fraction. So we can do experiments with white roofs. On the left, you are seeing the ACS computed through this by the model. You can see that it varies spatially across the entire Earth, right? On the right, you are seeing the surface energy balance model results. It's not perfect match because it's a linear model, but you can see that the linear model captures quite a bit of the pattern that you see simulated by the CL. And more importantly, you can start to ask questions about, which lambda is more important in this problem. And through that, you can actually learn a little bit about heat transfer. So let's start with the familiar lambda ELW, which is the emitted long wave radiation. This is the Planck feedback parameter. Its value is about 6 watts per square meter per Kelvin. Again, this is the surface one. This is not the global. This is not the Planck feedback parameter used in climate literature, which there it was about 3 watts per square meter per Kelvin. Here it's 6 watts per square meter per Kelvin because the surface temperature is about 300 Kelvin. If you use 300 Kelvin, your Planck feedback parameter is about 6 watts per square meter. The second one, I'll talk about this one first, is the convective transfer efficiency. Its value is much larger. You can see that almost 3 times larger. It's on the order of like 18 to 20 watts per square meter per Kelvin. If you remember, in the Wolf simulation, it's also about 18 to 20 watts per square meter per Kelvin. And it also doesn't change much globally. Well, the other two lambdas, one associated with latent heat transfer, the other associated with conductive heat transfer, they vary quite a lot spatially. For the latent heat transfer, you can imagine that the reason that the roof produces latent heat flux or evaporation is mostly because of rain. After rainfall, the roof holds some water, and the holding water gets evaporated afterward. So in a climatological sense, by the way, these are climate simulations. These have been, simulated over 20 years, averaged in the June, July, August summer season. So this is like climatological assessment of white cloud effect. So in certain places, you see very high values. In other places, you see low values. And it turns out that this pattern looks almost exactly like the rainfall pattern on land in those 3 months. So in places where you see a lot more rain, the roof holds more water, and the roof, as a result, evaporates more water. The conductive heat transfer efficiency is related to the roof material, in particular, heat capacity and the thermal conductivity of the roof. And those are model inputs, except in a few places where this model data developer seems to think that the roof is essentially made of metal, so conduction is very efficient. So those red color spots. Elsewhere, the conductive heat transfer efficiency is much smaller, at least the compared to convective. So globally, you can say the convective heat transfer efficiency is still quite important. It's, in terms of magnitude, it's probably the most important one. But in terms of spatial variability, you can see that now the latent heat transfer and the conductive heat transfer becomes important depending on your local meteorology, so rain, depending also on the building materials, like the water holding capacity of the roof, as well as the thermal properties of the roof. So to summarize this part a little bit, hopefully I've showed you that this white roof problem is revisited using a local surface climate sensitivity concept, ACS. And with a linearized surface energy balance model, we are able to connect the local climate surface climate sensitivity to the feedback parameters. Among all these heat transfer efficiencies or feedback parameters, the convective one is the key in both the Boston simulation as well as the global simulation. And this new concept is not meant to replace AC value or AC concept. It's meant to be a stepping stone for us to understand AC. As I argued very early on, the reason we want to focus on the surface, the reason we want to focus on the surface temperature and also to figure out the variability of the surface is because the cooling signal is coming from the surface. We have to be able to understand the surface changes before we understand the near surface air changes, which tend to be more complicated. Okay, now I want to move to the second part, which is the opposite. So instead of making the cities cooler, now we are making cities hotter. And the problem is related to the anthropogenic heat flux, which is the energy or the heat flux generated by human activities, such as using air conditioning. We dump the exhaust heat into the urban canyon, which essentially heat the urban system. The anthropogenic heat flux, from a measurement perspective, cannot be really separated from the traditional sensible heat flux. There's no way to really separate that from a purely observational perspective. As a result, to isolate the effect of anthropogenic heat flux, we almost have to do numeric experiments. And that's how people have been doing that for decades. You can see that this is an incomplete list of the previous studies looking at anthropogenic heat flux effects. Different people are using different numeric models over different cities. They prescribe different amount of anthropogenic heat flux because in those different cities, they have different amount of human activity levels. And they got different temperature changes, as you would expect. This table is a classic, or in my opinion, is the perfect example of approaching the problem from a applied perspective, right? It's almost like, the city government asks you to figure out the warming effect of anthropogenic heat flux in my city. And what you do is you take the energy consumption data from the city, you digitize that, you put that as the heat flux into the numeric model, you run the model, you figure out how much warming effect you get, you report to the city official, okay, that's the warming effect that we have experienced due to the anthropogenic heat flux. But from a more scientific perspective, or this is the table that my postdoc showed me actually, and the first question I asked her is like, I don't think we should focus on the change of the air temperature, because the change of the air temperature obviously is related to the amount of anthropogenic heat flux that you put into the model. The more you put into the model, the hotter the model becomes. It's that simple from a physics perspective, right? If you put 1,000 watts per square meter, it must be warmer more than putting in 100 watts per square meter. So I told her, well, let's normalize the temperature by the anthropogenic heat flux. You have to take the ratio of the two. If you take the ratio of the two, you can see first the unit changes. Instead of focusing on Kelvin, we're focusing on something that is defined in the unit of Kelvin per watts per square meter, just like the local climate sensitivity that we did in the first example. Second, you actually see some consistency across now these different studies. The values are not always, but on the order of like 0.01 Kelvin per watts per square meter across all these different studies, which is pretty actually remarkable given that they're using different models, different cities, different amount of anthropogenic heat flux. But of course, there are still variability in this new index. And the question is, what's causing the variability of this new index? And to understand this variability, for example, one of the, some of these studies, if you read them closely, you will find that anthropogenic heat flux tend to be stronger in the winter than in the summer. So if you put in the same amount of anthropogenic heat flux in the winter, the warming effect tends to be stronger than in the summer. And, the question is, well, why is that? Well, intuitively, it's probably understandable, but, can we actually quantify what are the reasons that cause this seasonal variability, as well as spatial variability? In Boston, it might be different from LA. Okay, so I'm going to use almost the same approach that I did early on, except now I'm focusing on the canopy air energy balance instead of the surface energy balance. I'm still using kind of like a urban canyon structure type of idea because my job is to diagnose the model outputs. And in this case, we're looking at the energy balance of the urban canopy air, which we assume has 0 heat capacity, so it cannot hold any energy, just like we assume this roof surface is infinite thing. So the energy in has to be equal to the energy out. Otherwise, the system blows up. The energy in is the anthropogenic heat flux. You cannot see it here. It's basically this red arrow. That's the anthropogenic heat flux we put into the urban canyon air. The energy out of this system, because the canopy air is a fluid, so the only way to take the energy out is either through convection or through radiation. But within this small domain, we usually ignore the radiation. So there are essentially two convective heat fluxes that take the energy out of the system. One is to the upper atmosphere, one is to the surface, and we can use the bulk formulation to parameterize the sensible heat flux, which we showed earlier. Rho Cp, again, is the air density heat capacity of air, and then some heat transfer coefficient or conductance multiplied by the temperature difference. This TA is the canopy air temperature. This theta ATM is the atmospheric boundary layer model. So you can see that the first flux is going up. The second one is going from the canopy air to the surface. That's the energy balance. If you look at the energy balance on the right-hand side of the equation, you can already see that it's just a linear function of the canopy air temperature TA. So you can essentially reorganize the equation, make it like the anthropogenic heat flux is equal to some lambda 0 multiplied by the canopy air temperature plus some C0. The linear function. Lambda again represents the slope, phi represents the intercept, and this lambda 0 and C0 can be, reorganized from the equation. You can again, using the graph that we showed earlier to study this problem, you are plotting both sides of the equations as a function of the canopy air temperature. The anthropogenic heat flux is not a function of the canopy air temperature because it's a prescribed input into the model. The right-hand side equation is a linear function of the canopy air temperature, so it's represented by this red line. Now everyone hopefully understands now the canopy air temperature has to be at this intersection, because it is only at this intersection that the left-hand side equation is equal to the right-hand side equation, or the energy is in balance. Now if you raise the anthropogenic heat flux, you bring up the black line instead of bringing down the black line, you get a new intersection, in this case an increased canopy air temperature. And in this model, you can see that is the flux divided by lambda 0, which is the slope of the red line. So this is the convectivity transfer coefficient. In this case, you only have one lambda, which is the convectivity, right? And that's the simple model that we had. And it turns out that this simple model cannot explain the spatial, the seasonal variability, as I will show you in a minute. So we need to make this model a bit more complicated. How? We want to break down one more assumption. So far, in the two examples that I showed, I have always assumed this red line stays where it is. What if this red line does not stay where it is? For example, as you put in the anthropogenic heat flux in your model, the red line used to be this in the control run, and then in your sensitivity one, the red line starts to change and it becomes this blue line, which is very possible because the slope of this line depends on the lambda, and the lambda is the convectivity transfer, and the convectivity transfer is related to the thermal stratification of the atmosphere. If you put in anthropogenic heat flux, you make the atmosphere more unstable, you alter the convectivity transfer efficiency, you make the convectivity transfer a bit more efficient. So the red line becomes the blue line. Suddenly, you can see that the warming signal used to be this red arrow, becomes this blue arrow. So effectively, we introduce a negative feedback into the system that reduces the warming signal that you would have without this feedback. And intuitively, what does this represent? It basically represents, as you put anthropogenic heat flux into the urban canyon, the wind or the turbulence ventilates the heat out of the canyon. The more you put it in, the ventilation effect gets enhanced a little bit more. So without this enhancement, the warming signal will be a lot stronger than with this ventilation effect. So how can let's think through this problem a bit more. We know the problem is like we have the climate forcing, which is the anthropogenic heat flux. It's a very simple problem. We know the baseline scenario, just like kind of like the Planck feedback. The canopy air increases temperature, so it convects the heat elsewhere in order to balance the anthropogenic heat flux. But as this process goes on, there are other feedbacks come into play. For example, the conductance change or the convectivity transfer efficiency that we just mentioned. In this case, we have two of them. One goes to the atmosphere, one goes to the surface. The surface temperature will also change as you put it into the anthropogenic heat flux. The heat, you have convecting more heat to the surface temperature increase. As the surface temperature increase, the canopy air temperature will further increase. The atmospheric temperature might also respond, and this would be related to large-scale atmospheric feedback. But we can exclude that for now, for example, through doing just land-only experiments without coupling it to the atmosphere. So in the next, I want to show you how we actually use numeric simulations to diagnose these three different feedback parameters. And I have, I want to work through all of how we diagnose this feedback. So I only have three equations, so bear with me. The first equation says that if you change the anthropogenic heat flux on the left-hand side equation, the right-hand side equation has to be changed in the same way. Otherwise, the system is no longer in energy balance. And I'm going to denote the right-hand side equation as minus R. It's just a notation. As a result, the climate sensitivity that I'm looking for, which is the change of the canopy air temperature divided by the sensible anthropogenic heat flux, is the change of the temperature divided by minus dot R, just from this location. And I can put the change of the temperature into the denominator. And this is the total feedback parameter. So you can see that the climate sensitivity is the inverse of the climate feedback, similar to the climate change literature. The only difference between this example and the White example is that I introduce a negative sign here. You don't have to introduce the negative sign, it's just for notation purpose. And then you use the so-called chain rule in calculus to express the total change into the partial derivative, which is the baseline response, that assuming everything else stays the same, the only change is the canopy air temperature. And then you have the feedback from other things. If you change the canopy air temperature, the surface temperature changes, the two heat transfer efficiencies also change, or the conductances change. So using this, you can diagnose the contributions of all these different feedback parameters and use that to understand the sensitivity of the canopy air temperature to the anthropogenic heat. So let me show you some results. These are the simulations that we did over Camas at a resolution of 1/8 degrees, about 12.5 kilometers. You probably cannot see the spatial variability. So I'm simply going to ask you to focus on the values on the top right. And those are the median values across Camas. If you see a color, it means that it has, again, an urban grid. It's an urban grid cell. It has urban fractions. If you don't see a color, it means it's either ocean or land areas without city. But just focus on the values in the top right. So everything that you see is not climate sensitivity, it's climate feedback parameter. So the non-matter will be climate. In the first one, you are seeing the total feedback parameter. On the left is the summer season, June, July, August. On the right is the winter season. So you can see that, first of all, you can see that the total feedback parameter is on the order of 100 watts per square meter per Kelvin. One is about 122, one is about 111, of course with the minus sign. And the minus sign here means it's negative feedback. You don't have to worry about the negative sign. Well, the reason that it's 100 is good because the climate sensitivity is inverse of it. So if it's the total feedback parameter is about 100 watts per square meter, then the sensitivity is on the order of 0.01 Kelvin per square meter, which is exactly the number that you get from combining all the literature studies. You get about 0.01 Kelvin per square meter, which is good, right? Second, if you look at the feedback parameter, it's a bit, in terms of the magnitude, it's smaller in the winter than in the summer, which means the sensitivity is larger in the winter than in the summer, which is also consistent with the literature. In the winter, if you put the same amount of anthropogenic heat flux into the model, you get more cooling, more warming than in the summer. But what's causing this summer-winter difference? It's not because of the baseline. You can see that the baseline is almost the same between summer and winter. And the baseline is actually almost the same as the total in the summer, which means that the baseline is a good estimate of the total feedback parameter, especially in the summer. So again, if you know the baseline scenario, which is the red line states where it is scenario, you know half of the story. You don't need to make the story more complicated. It's already like half done, except that you cannot explain the seasonal variability. To explain the seasonal variability, you really need to introduce this new feedback parameters that I mentioned earlier. One is from the surface temperature, one is from the conductance between the canopy L and the atmosphere L above it. The surface temperature is a positive feedback, so the feedback parameters are positive. The second one is a negative feedback parameter, which is the heat conductance, which is basically this red line becomes the blue line, so it reduces the warming effect. You can see that the two almost cancel each other in the summer, but in the winter, the negative feedback from the heat transfer efficiency, convective heat transfer, is inhibited. As a result, the positive feedback wins over, which is why in the winter, the climate sensitivity tends to be a bit stronger because of this stronger surface temperature feedback that wins over the negative feedback. The last one is that the heat transfer between the canopy and the surface shows almost negligible contribution. And this is because in the model, this heat transfer is not parameterized as a function of the thermal stratification, which is why its contribution is also negligible. It's actually reassuring because we know that this heat transfer should not be strongly affected by anthropogenic heat, and the diagnostic method does indeed show that its contribution is negligible. So now we have, all the results here. We now understand why the sensitivity is on the 0.01 Kelvin per watts per square meter. We understand that it's mostly coming from the baseline scenario. And we also understand that the seasonal variability is related to the inhibition of the negative feedback from the canyon to the atmosphere. So hopefully, with these two examples, I convince you that these linearized energy balance models are quite useful for us to understand these simulated changes, especially related to surface and near surface air temperatures. And in all the examples studied here, convective heat transfer is the key, but its parameterization remains a challenge. In the first example is the convective heat transfer from the roof. In the second example is the convective transfer from the canyon, and both are very poorly represented in numerical models. So this is related to the other side of my research, which focuses more on the fluid dynamics in cities. But the takeaway message for this presentation is that I think concepts like climate forcing, sensitivity, and feedback should really be embraced in urban modeling research. I think they really help us to reframe our question and redesign our numeric experiments. With that, I'll stop and I'm happy to take questions.
好的，那我们就非常感谢您，那个李丹教授很精彩的报告，从10点的1个小时整，然后给我们很细致、很深入的来这个做了这方面的一些介绍。然后我看，然后刚好在咱们那个群里面，在那个群里，然后就是廖威林老师刚把那个温故读新发了一篇那个这个温故读新第5篇，然后这个其中第2篇，然后就刚好是这个李老师这一篇文章，是在2025年这个就是在 IRC 就是地球物理研究上面的是吧？这篇文章，然后就刚好给了一个比较详细的一个这篇文章的一个介绍，对。然后大家如果是有兴趣呢，也可以去在这个看一下相关的一些文字和介绍。然后那我们下面看看大家有没有什么一些问题可以做进一步的交流。还有咱们线上的呢，也可以通过文字或者是这个直接可以把话筒打开可以讲。那我们先看一下咱们就是咱们线下老师。
第一个问题就是提到这个
是应用科学和应用气象和气候科学的理论，它们之间的一个连接。就是我听了您的报告，大概懂的这个意思，但是我觉得还是不理解的可能不是很到位，所以我想问一下，就是应用科学和气候科学它们之间有什么，就是从思路和研究方法上，它们有什么不一样？然后需要我们建立这样的一个联系。
其实我也未必回答特别好，因为这已经有一点哲学的意思。在我的理解里面，我觉得这个就是单说 applied meteorology， 但是每个学科都有从 applied 的角度来研究，数学这个 applied math 和 pure math， 我们其实我也是从这个角度来 applied meteorology 就是为了解决。我们有工具，有理论，我可以解决这个问题，那我就可以解决。比如说我们这个 anthropogenic heat flash， 如果你有北京的 anthropogenic heat flash 的数据，你有这个相应的模型能够模拟这个 anthropogenic heat flash effect， 你就可以拿来这个数据放到这个模型，你就可以得出来你觉得这个北京的 anthropogenic heat flash 造成了多大的影响。如果你止步在这里，这其实就是一个 applied meteorology 已经很完善的问题，就是我们已经解决了。但是在我看来，如果是从一个 science 的角度来研究问题的话，我们更想要知道的是一些更 universal 的。就我并不想知道这个 anthropogenic flag 在北京，我想知道这个 anthropogenic flag 在北京、在上海、在波士顿、在 LA， 他们的 effect 有什么样的不一样？为什么不一样？我能不能总结出一些更普适性的规律，使得我能够帮助我能够理解为什么在北京是这样，为什么在上海是这样，波士顿是这样？能明白这个？就是
刚刚这点是您做的这两个工作，就是把它们就是解析，然后来解释这个部分，是吧？就是这个是不是？
对，就是我们这个我自己的研究的这个方向，就是从可能前面我读 PhD 和读 Postdoc 做的这个研究，主要是从这个 applied 怎么样去这个提高我们 improve 我们这个模型啊，这个加一点新的参数化方案呀，使得我们能够解决这个问题。但我们现在更重要的就是要不光解决这个问题，我还要理解为什么出现了这样一个问题。
那我的第二个问题就是，我中间有一点不理解，就是第一部分里面那个在解释它的那个白物体的冷却效应和冷却效应它为什么不一样的时候，就是后面我们解释的时候是可弱不等的突然，然后它的几个参数它在不同的季节的不同地方表现出来不一样的。然后我不太明白的就是您前面这个例子是波士顿的例子。就是在波士顿这样一个非常落后的一个范围之内，它出现了正差异，这是一个很大的变化。就是在那么小的范围之内，它是会有这么大的就是变化的，尤其是那两个就是不同区域变化不一样的那个参数，一个和降水有关系，和一些气象要素有关系。但是在波士顿的这个范围之内，是这个原因造成的。就是我的意思是说，波士顿范围毕竟是太平地方，就是它对于全球或相对于一个区域来说，它是一个城市的。就是它降水会有这么大的差异吗？然后是它其他的要素有大差异导致您一开始得到的那个具体的那个
对抗
对，它有正负的差异。
你可能把这两个有一点混淆，就是那个出现正负是当你看的这个是这个大气的。你看这个大气的时候出现正负，是因为在有些地方它出现了一些大气的一些响应。
明白。
就是尽管你地表在铺荡，但是你大气的响应是一个在这个地方是一个 warming 的地方，所以使得你在这个地方看到一个 warming， 就是你引发了一些 warm air convection， 就从别的地方就。
就是你后面解释的其实是对于只不是对。
对，后面的解释都是针对的这个消费，因为我的观点是我们一定要 先要能解释这个 surface， 才能够解释这个 meteorology。否则的话，如果我们连 surface tension 这个 variability 都搞不明白的话，那我们怎么可能能够搞明白这个 meteorology？
这个过程很复杂，很期待着以后的如果能够
对，这也是我们最近一段时间在做的。
那个，然后就是中大的那个梅老师问说，第8页的温度的扩线是对数律的理论基础。
温度的扩线的话，它在那个我放的这个扩线就是在 surface 和大气 model 的底层，所以这个我们叫 surface atmospheric surface layer。atmospheric surface layer 的 profile 在近中性的时候对于 scalar 对于 temperature 和 humidity 应该都是对数的，这个就是 Monod-Bukov similarity theory 就是它的理论基础就是 Monod-Bukov similarity theory。当然了，在实际情况下的话，它肯定不是近中性，所以我画的那个对数率之所以画成对数，其实它也只是一个简化，想告诉大家就是它应该可能长的是对数的，但是并不一定完全是对的。
这个应该是澳门大学的那个，就是高亮老师说，如果将这个方法用在比较小的尺度和解析度，能有效捕捉城市风场、温度和湿度吗？如何验证模型和参数？误差来源会主要来自哪里？
这个还没有办法用到这个比较小的，在我看，因为如果在空间比较小和时间比较小的时候，在时间比较小的尺度上的时候，这些做的这些线性化的假设，它就不是特别的成立的。在空间比较小的时候呢，在空间比较小的时候的话，这空间比较小的时候，其实并不是这个 diagnostic 模型有问题啊。在空间比较小的话，应该是属于这个原本的这个模型就已经不太适用了。就比方说，我这个有个 lambda h， 我这个 lambda h 在模型里面，它原本就是按照一个比较大的空间尺度来用，来参数化的。然后你用在了一个比较小的空间尺度上面，这个 lambda h 可能自己就不是特别的准。所以这个用在比较小的空间尺度上面，并不是我们这个 diagnostic 这个模型的问题，主要还是这个 prognostic， 就是你原本的那个模型就会出现一些比较重要的，就会出现问题。所以我们这个我今天讲的主要是，在你已经有这个 prognostic 模型的时候，我们怎么用一些简单的这个 diagnostic 的方法，能够帮助你理解你这个 prognostic 模型出来的这个结果。
好的，很难
梅老师，就是你这个问题，对比没办法刷期嘛，如果我们刷的厚不一样的话，就这个问题。
在实际上的话，肯定会有影响，对吧？因为你刷的厚度不一样的话，也许它这个 albedo 的变化就不一样。但是从这个数学的角度来算的话，你是没有影响，因为你只要知道这个前后它这个 albedo 的变化多少，你就能够用这个。
明白，但是实际当中没跟上，稍微厚一点。
这是一个好问题，因为你刷厚了一点呢，你可能就不光光只改变了 LB， 你可能还改变了别的东西，你要把那个杂才要考虑。比如说你可能改变了 heat capacity， 对，你要这样考虑。当我这个 roof 就是比如说 everything else stays the same， 就是 LB 的也是的，但是我只改变那个热容量的时候，它又会发生什么？就比方说光伏，其实它就有一点类似一样，就是它不光改变了 albedo， 它也改变了很多其余的很多东西。这样的话，你也可以处理，因为像这些模型的话，你可以研究的这个 perturbation 是由于一个东西造成的，你也可以研究它是由不同的东西同时找到。
因为现在研究比较多，就是也不能说比较多嘛，就是白色屋顶、绿色屋顶，但是这些研究屋顶的这种路上行人的一个舒适度的影响，就是我是觉得影响并不是那么大，我们应该更关注一些垂直立面的墙体的，一些墙体，这种可能 比关注楼顶的这个降温的特点会对行人更有帮助。
是的，但你说的这个问题已经就不是我要讲的，是单从这个做 prediction 的，就是说这个问题就是这个模型还该不该用？就是10年前、20年前，就没有说我还在做这种研究，就是做这种 model development 的时候，肯定是应该用，因为在当时这就是最前沿。但在这个时候的那2025年的话，确实有更好的手段，对吧？比如说我们可以做很少街区的 CFD，而现在的 CFD 都已经跟 WRF cover 的很好了，不光是风场，它这个那个 radiation 啊、thermal 的这个 cover 也很好。所以这个时候，比如我们组里面现在也在做，就是用 LES 算出来这个 white effect 和用 WRF 算出来这个 white effect 有什么区别？然后你怎么去理解它这个两个的区别？比如 WRF 算出来是负0.2，那个算出来只有负0.1，就是为什么？是不是因为在 WRF 里面你的这个 roof 直接就跟你的大气的连接在一起，你不 resolve 这个方法，你在你的 LES 里面你要 resolve 这个方法这就是又是一个 applied。然后这个 applied 问题你做多了之后，那接下来你又要回到这个，那我们是不是就可以知道，比如说我如果知道我这个 building 的 distribution vertical height 的 distribution， 我就可以能够 infer 出来，在这个 white roof， 在比如说这一层这样高度的 building 做了 white roof， 这样高度的 building 做了 white roof， 我这个底下在这个2米的这个比如说行人走来走，就能感受到多的这个空气的这个效果。如果你能你做了足够多的 apply 这个问题的话，你又可以回到这个 universal 的问题，就是我们能不能就是不需要再做这么多实验，然后能够就回答这些这个问题。
这个问题是您后边讲到出现那个器官也会对地表的影响。就是现在我们就是如果用遥感，现在好多研究用遥感的地表温度来模拟这个来规范气温，来规范气温热感。就如果是说考虑气温也对地表温度有影响的话，那我们这个研究就有点有生物差感。
你把这个你把情况再说。
就是现在有些研究是用微细遥感的地表温度来去估算这个气温和点的气温，因为这个地表温度是比较反干涉的，
对，
然后对气温也会对地表温度有影响。其实这个地表温度是一个不光是地表下界面类型变化导致的这个变化，还有气温对它这个变化。那我们如果用遥感的这个综合的地表温度再去估算这个气温，这个
它这个应该不叫误差，会有 challenge， 就是因为地表，就像你刚刚说的，你地表的温度受到这个地表的这个种类影响很大，就是你这边是树啊，是草啊，对。
对，我的意思是
这是草，对，等一下，
对，所以
就是从关注的这个地表温度来区分它到底是气温影响的地表温度变化，还是地表下界面类型的。
那是做不到，因为你只能看到这个 final outcome， 你说不出来这个大气的温度的，比如说大气温度的 variability 对地表温度的 variability， 就是这个效应，你只能看到这两个 variability， 它们俩在现实中可能是有一定的关系，但是并不一定是非常强烈的关系。然后它们俩之间的区别还主要取决于就是我刚刚说的这个 convective transfer。所以，所以如果你的问题是你在遥感能看到地表的温度，然后你要通过地表的温度来反算大气的温度，很多人是可以的，而且这个是有一定的理论基础。但是你的地表温度的 spatial pattern 和你的大气的温度的 spatial pattern 肯定不是一样的，而它们的不一样就取决于你这个 convective transfer 在这个地方有。
还有一个问题就是跳出于你的研究内容这个，就是你像现在遥感的话，也可以为这些数字模型提供一些下界面的参数，还有大气的一些参数。但是遥感有一个局限，就是说遥感只能到某一个角度来分析， 对吧？但是我们实际上是一个，其实它是一个更加三维的这个东西。所以说，我想问您对这个遥感的方向的这个方向来增入这个模型的模拟的发展。
我并没有很多建议，因为前不久那个跟几个老师做地理的也做遥感的也跟他们这个有一些合作，这首先从不同的角度你能看到，如果你真的只是 LV 的话，我觉得是用不了就弄那么混，因为从某种角度你给我这种信息，我也未必能用得上。如果三维的角度，如果你说的是整个城市的这个所有的地理信息，这个楼长得什么样啊，这个树长得怎么样，在哪呀？那些是很有用，那些的话你当然能够用到更精细的数据模型，但是我们现在拥有的这个数据模型，像沃虎，你没有办法去把这样的信息给吃进来。这个我们中央大学的廖梦宁老师前几天做了个报告，就是讲他们做了一个特别好的数据给沃虎，但放到沃虎里面，一方面沃虎根本不需要这么多数据，二者你放进去之后，可能这个效果还特别不好，所以两边都需要努力吧。就是一方面，这个我们需要有更精细的这个地表的数据、地理的数据，但另外一方面，我们也要有一些更好的这个那个手段，能够把这些数据的用起来。
就是你讲到一个人为热对气温的影响，其实在城市里边这个热储量其实也很大。就是这一块儿，因为我们曾经也做了一个工作，就是用卫星遥感的近卫星遥感1小时的温度的一个变化，去模拟了一个城市的热储量的一个可点的一个数据，发现它对气温的相关性是非常大的，特别是在夜间0.95以上，然后白天是比较低的0.1左右。所以说，
这是正，这是很合乎这个 textbook 这个内容的这个结果。
对，但是我们现在是近卫星，我们是用的单表的，所以我们接下来是会用一个把它弄成一个三维的角度再去跟气温做对比，那也有了一个结果，发现就是不同角度的卫星的地表温度去反映的这个热储量跟气温相关性，发现就是等效的三维的温度出来的热储量，也就是说三维的热储量跟气温的相关性是更大的。
那就说明这个三维的信息还是有用的，挺好的。我来回答一下王伟的。
好。
回
答王伟老师说，第一个就是大家都从垂直一维的地表能量图层来做诊断，就是觉得水平停留过程需要考虑吗？第二是大规模的白色污点可能会改变对流的动力过程，目前考虑了动力过程引起的天气变化，有没有考虑这个天气变化？也就是路面大气耦合在一起。
我先来回答第二个问题吧。第二个问题的话，我们做了这个路面和大气耦合在沃夫里面都是耦合在一起的。这个全球的我们也做了这个耦合在一起，以及没有耦合在一起。这个大规模的白色污点在你长时间的 simulation 里面可能会对这个天气会对天气产生一定的影响。但这方面的影响的话，在我现在看到的结果基本上还是一个小量，就是它还不是一个就是你也可以认为这个是个 feedback， 但我觉得这个 feedback 的这个信号这个 feedback 并没有特别的强。但这个 feedback 它是一个 scale dependent， 这个是一个比较麻烦的事情，就是如果你的这个模型的这个 resolution 发生变化，你的这个 analysis 的这个 domain 发生变化的话，它也许就发生了重大的变化。就举个极端的例子，你如果在北京的北部那个你有了这个 white roof 之后，它开始云就这个地方增加的特别多，那这个地方的这个从云过来的 feedback 就会很重要。这就回到了一个更大的问题，就是我们要不要做这样的事情。就是这个云的 feedback 这个 uncertainty 有几 我就不去展开讲。第一个就是从垂直一维的来做能量平衡的诊断，这个 advective heat 很重要，尤其是对于这个大气，这也就是为什么我觉得我们不能上来就研究这个大气。我们如果上来就研究这个 near surface air temperature 或者说这个 atmospheric simulated temperature 的变化的话，那你就一定要面对这个 advective heat 的这个问题。如果你要avoid 这个问题，你就要先从这个 surface 的角度。你如果先从 surface 角度来讲的话，那你就会发现这个水平的这个那个平面过程的话，对于这个 diagnose 这个 surface temperature change 并不是一个并不是绝对需要的。
好的，后面这个问题我觉得比较大啊，就是他是回答，他是回答这个张恒恒老师同学，所以说是第一个是团流是不是可预测，第二个是在大规模地中初始的团流导致一个随机数，那如何在此后的预测能够保证团流是正确？通过团流闭合方程吗？
第一个是团流是可以预测的，这你不能预测团流每个时刻长成什么样，但是你可以预测团流的这个我们叫 statistics。第二个问题的话，
这我来答哪个？
既然初始的那个团流场是个随机数，你不需要保证这个团流是正确的，因为它既然是个随机的，它就自然而然它的这个初始条件就对你的结果就不会影响特别大。这个我们叫就是这个我们要尽量的让这个初始条件不影响你的这个结果。
看挺好的，现在已经11:26，大概还有那么几分钟，大家如果还有问题的话可以再问一下。还有问题吗？
我问一个特别简单的问题，
好，一个短的，
就您那个第二项 T2的那个解构，那个叫 decomposition，这个是具体是怎么做的？
这个有最简单的方法就是你把 work 里面算 T2 exactly reproduce 出来，就是 work 怎么算的你就怎么算。work 需要哪些参数你都给它 output，然后你每一次 replace 就是比如你 control 上有个 T2，然后这个 T2 肯定是跟你的 roof surface temperature 跟你的 wall temperature 跟你所有的很多东西都有关系，你把那些东西都要保证。然后你每次就换一次。你就换到了这个 sensitivity 上，我如果只把这个 roof temperature 换，只把这个 air temperature 换，只把这个多大的 temperature，这是最简单的。当然更复杂的话，你可以直接就是去导标准，那个可能就没有太大的必要。你如果我们那个 code 和东西你都能找，你可以看到我行不行？好，也就是你看到需要 output 的哪些东西，你就可以去就可以这个看。最关键的就是你在这个，就比方说 T2 就是一个 function A and B， 就是两个东西。那你第一次算的时候，你control run 是 F 等于 A 和 B， 然后你这个这个是 A2 B2， 那你还可以算一个 F A B2 和 A2 B， 就是这样。所以它这个 decomposition 也是个线性的，因为它加起来之后不会等于最后的，这也是为什么你看它们加起来的 total 不会等于这个 work。
挺好的，那我们就非常感谢雷老师很精彩的报告，就是也是给了我们一个从这个应用到科学研究，这样就是说怎么样来一步一步的来开展这样一个深入的科学研究，这样一个很好的一个范例。然后呢，我们如果后面有问题可以再做进一步的，然后可以再和雷老师做进一步的讨论。那我们今天上午的报告就到这儿，谢谢大家。关那个。